This section will be on section 2.3, which is on continuity. And the main topics of this section: continuity of a function, what it means, why it's important, and then the main thing we want to do here in this section is solving inequalities using continuity. So this will be built on our limits, but it's not nearly as thorough. You got through the main hard part of limits in 2.1 and 2.2. The main thing we want to do in this section is something that's very important in chapter 4 that we'll do in almost every problem: solving inequalities. So we'll see how to do that at the end. All right, so continuity of a function is an important feature. We will see it as a requirement for virtually all problems of interest that use calculus. We begin by defining what it means for a function to be continuous. We'll look at a visual representation and then an easy way, quote unquote, easy way to figure out where a function is continuous. So what we have here, it says let f be a function and c be a number in the domain of f, which means once again, we can just plug it in. Then we say f is continuous at x equals c if the limit as x goes to c of f of x equals f of c. So, we had examples before where this number for the limit was different than this number. To be continuous, we need them to be the same. What we can kind of think about here is the graph, which we'll see from examples, is attached on both sides. So there's not a gap like there is here. You can kind of peek down to the picture below. And the closed circle is on the graph, which you might not actually see a closed circle. It's just part of a graph. But we will look at a couple examples so you can see. Actually, we have 4 examples. Plenty of examples to see what's going on here. All right, so part A and B deal with x equals -2. We want to find the limit as x goes to -2 of f of x, and then what f of -2 is. This is -1, this is -2, and we want to look here for part A. And what is the limit as x goes to -2? Well, what's the y value as we walk towards this point on the graph? Well, we're walking towards 2 from both sides. All right, we have to go from both sides. We have to be sure we remember that. It's going towards y equals 2 from both sides. And then f of -2, remember that's where the closed circle is. The closed circle at -2 is up here, and the y value is 3. So f of -2 equals 3. Right, what we would say here, even though we're not specifically asked it the way it's written, but is it continuous at -2? The answer is no, it's not continuous at x equals -2 because they are different. Right, one way a lot of people like to explain continuity, and I think it's a good way to explain it as well, is if you can draw the picture without lifting up your pencil at a point. Oops, let me do that. All right, so here, if we're drawing our picture, we have to lift it up to make this point here at -2. If we are just trying to draw this picture, we have to lift it up in a lot of spots, but at -2 specifically. We also have to lift it up to make the circle. So even if this wasn't there, the answer would be no. Okay. All right, so the next one we are interested in is -1, x equals -1. And what is the limit as x goes to -1? Well, from both ways we are approaching 0. If we come at -1 from the left, we are going towards 0. And -1 from the right, we're also going towards y equals 0. And then what is the function value at -1? Well, that's also 0. You notice that there's not a circle there. That means it's like an invisible filled in circle. F of -1 is also 0. All right, so what that's telling us, it is continuous at x equals 1. -1, not 1. Because these numbers are the same. But once again, if you kind of think about what I said about drawing the picture, we don't have to lift our pencil up to draw the picture. There's no hole here. We just make our V shaped. We can keep our pencil on the paper. We're good to go. All right, so the next part we're interested in is at x equals 1, which is right here. What's the limit as x goes to 1? Well, we've had plenty of practice now to know that this one does not exist because we're going up here from the left to this y value of 3, and from the right we're going down to y equals 0. So this is D and E. And then what is the function value? This was a filled in circle here. So f of 1 equals 0. Right, now these are different, which makes it not continuous at 1, but it's automatically not continuous if the limit doesn't exist. Right, if they're both D and E, then you might think, well, that's the same, but that's not the same. They have to be the same number. If even one of them is D and E, then it's bad. Okay, and then the last number we are interested in is at x equals 2, which is right here. I don't know why I didn't fill in the rest. Just doing that real quick. All right, but if we look at the limit going towards x equals 2, we see that that does exist. If we're going towards 2 from the left and 2 from the right, we're going towards y equals 1 both ways. But what you want to notice here is that we have a hole and we don't have any filled in circles above or below, which means f of 2 is D and E. And once again, when one of the two is D and E, that means it's not continuous. It doesn't matter which one is not D and E. So it's not continuous at x equals 2, since f of 2 does not exist. They're not the same. But also, if you think about drawing this, you might think, well, I can draw this without lifting up my pencil. Technically, you're supposed to, when you hand draw, you're supposed to make the circle yourself. Anytime there's a circle, you're kind of like skipping over a spot. But that's the idea of continuity. What I want to point out here, we didn't talk about any other points like 3. 3, it's continuous at 3 because we're just going on through it. It's continuous at 0 because we're just passing through it. We can draw that and all the other numbers in between. So what's more important for us in the rest of the course is being able to know when a function is continuous looking at its formula. Alright, so when given a formula, determining where a function is continuous is often important as well. There are two basic rules we will have to follow to determine where a function is continuous. Right, the first one is not one we really see at all in this class, but because we talked about piecewise functions, it's good to just mention them. If the function is not a piecewise defined function, the values the function is continuous is the same as the domain. Okay. Sorry, is not. I knew I forgot a word. So if the function is not continuous, is not a piecewise defined function, then the values of the function is continuous is the same as the domain. You learn how to figure out the domain in college algebra of things. We'll send a brief reminder when we do the problems, but that's if it's not piecewise. So if the function is piecewise, you must also check the values where the function value is separated. This is because we've already talked about piecewise functions often have graphs that look like pieces, meaning they are separated so they could look something like this, where you have this little section here and then the next little section is like this, and it's not continuous there. So you have to check where it's separated, and you have to lift up your pencil to draw each part. Alright, so what we're going to do in these couple of problems here, I only have two as you can see, because really there's not many other things we're going to need continuity for in this when we work through the class. We want to determine where the function p of x equals 12x to the fifth plus 4x minus 1 is continuous. Write your answer in interval notation. Alright, now one thing, if you look back, this is not piecewise, so we're really asking what is the domain. And the domain of a polynomial, which is what we're dealing with here, is always all real numbers. Right, we only have positive whole numbers as the powers of x, so it's a polynomial. And the way we write all real numbers in interval notation is negative infinity to infinity. And that is our answer for this one. There's no more work to do. Right, the second one, we have a rational function. Determine where the function m of x equals x plus 2 divided by x minus 2 times x minus 7 is continuous. Write your answer in interval notation. Once again, what is the domain? And one thing you should remember about the domain is if we have a fraction, the denominator cannot be 0. So we set the denominator equal to 0, we solve it, and then we throw those values away. We use all the rest. So let's go ahead and do that. Let's set this denominator equal to 0. We got x minus 2 times x minus 7 equals 0. It's already factored for us, which is very nice. We can set each part equal to 0. And then solve each one. The one on the left will get x equals 2. And the one on the right, we get x equals 7. Right, so remember, these are the values not in the domain. Everything else is. If you don't remember interval notation super well, when it comes to writing something like this, what you can do is mark off your numbers 2 and 7 on a number line. Since we are not using them, they get an open circle. And we want to use everything else. We want to use stuff to the left of 2. We want to use stuff in between 2 and 7. And we want to use the stuff to the right of 7. So we have 3 intervals here. The one on the left would be negative infinity up to 2. The one in the middle would be 2 to 7. And the one on the right would be 7 to infinity. And that's where this function is continuous. Now there are other functions that you learned about in college algebra. Since we don't know how to do limits with them yet, I'm talking about logarithms and exponents, stuff like that. We're not going to deal with them in this section. Their limits can be a little more challenging. So that is how we deal with continuity. One of the main reasons continuity is so important is when you solve inequalities, you look for spots where the function is equal to 0 or it's not continuous. All right, so let's go ahead and read it. One of the main uses of knowing where a function is continuous is this allows you to know we are solving inequalities the right way. The reason comes from the intermediate value theorem, which we will state below. All right, it's kind of confusing to read. I'm just going to read it. If you don't want to write it down, I'll summarize it as we work through the problems. Suppose f is a function which is not continuous at the numbers c1, c2 up to cn. So here would be 2 and 7 would be these values for this problem, and has x-intercepts of r1, r2 up to rm. So x-intercepts are when the numerator equals 0, which would be -2. Then the sign of f of x can only change at one of those points, where it's not continuous or where we have an x-intercept. The sign meaning from positive to negative. All right, so we will use the above to solve a couple inequalities. The main point here, find where the x-intercepts are and where the function is not continuous. When we get all these numbers, we will make a number line with these numbers. Right, and then we'll actually solve the problem afterwards. All right, so we want to solve the inequality x squared minus 4x minus 21 is less than 0 using a sign chart. That's what it will be called. Excuse me. Write your answer in interval notation. All right, so one thing that's very important when you do all these inequalities is make sure you have 0 on one side. Right, so if this was like 5 over here, we would subtract the 5 over to make sure we have 0. Right, now this one, I'll always save. Let's start with doing the x-intercepts. We set the numerator equal to 0. This thing doesn't have a fraction. It doesn't have a denominator. So really, for this one, we're just setting the whole thing equal to 0. All right, so what we're going to do is set the whole thing equal to 0. X squared minus 4x minus 21 equals 0, and solve this to get the x-intercepts. The x-intercepts are where the function equals 0, so that's why this makes sense. Right, so we can factor this. X minus 7 and x plus 3 work because -7 and 3 multiply to -21 and add to -4. Now we set each part equal to 0. We got x minus 7 equals 0 and x plus 3 equals 0. The one on the left, we get x equals 7. The one on the right, we get x equals negative 3. All right, now since we don't have a fraction, we don't have a denominator, there's no points where it's not continuous, we will make our number line marking off these numbers. All right, we don't want to add in any other numbers at all, just mark off negative 3 and 7. If you have a habit of putting in 0 in there, just to have it, don't put 0 in there, just plug in these two things. And now the idea of the sign chart is you take your original thing, we want to plug in numbers in each interval into this x squared minus 4x minus 21 and record the sign, whether it's positive or negative. So what I mean by each interval is we have to the left of 3, we can plug in like negative 4. Between negative 3 and 7, if you can plug in 0, I always recommend plugging in 0. It's the easiest thing to plug in. And then plug in something to the right of 7. You can plug in 8. So we want to plug in these three numbers in to x squared plus or minus 4x minus 21. We got f of negative 4. We got negative 4 squared minus 4 times negative 4 minus 21. You can get the exact number, or you can just remember what sign it is, positive or negative, because that's all that matters. So we got negative 4 squared minus 4 times negative 4 minus 21, which is 11. And what we care about is this is positive. So what I'm going to do on my sign chart, where when I plugged in negative 4, I got a positive number, I'm going to put a plus above it. And now I'm going to plug in 0 and 8 and do the same thing. So plug in 0, and we should get negative 21 because the first two things are 0, which is negative. I'm going to put a minus sign above the 0. And then the last thing I'm going to plug in is 8. So we got 8 squared minus 4 times 8 minus 21. And if you want to do that in your calculator, nothing wrong with that. Or do it by hand, doesn't matter. And we get 11. And it's not important. That's the same thing as this one. It's coincidental. What's important is we got a positive number. Okay. All right, so what's happening is in this interval from negative 3 to infinity, to negative 3, our thing is negative or positive. Between 3 and 7, it's negative. And between 7 and 8, 7 and infinity, it's positive. What you want to notice about our question here is we want negative. We want less than 0. And also there's no equal sign on the inequality, so use parentheses. So we only care about this section here then, where 0 is. 0 fits between negative 3 and 7, so that's what we care about. This is our answer. In interval notation, it's negative 3 to 7. We only care about the interval where it is negative. If this was flipped around, if it was greater than 0, we would use these two intervals. If you want, which I'll go ahead and do, we can graph and see this is not totally different from something we've done before. So let's go ahead and graph it. We have y equals x squared. Let me put it in the first one. Minus 4x minus 21. I'm going to hit zoom 6. And what it's asking us, if we're relating it back to inequalities we did before in the class, it's asking us where the graph is below the x-axis. -3 and 7, it's below the x-axis between -3 and 7, and it's above the x-axis to the left and to the right. That's exactly what our sign chart here is telling us. It's below the x-axis here, it's above the x-axis on these two portions. Right, but in general, you don't want to have to graph these, and this next one, as you can see, it's not a parabola. You might not know how to graph it. You wouldn't want to try to graph it. That's why we're going to do this new approach, using a sign chart. Okay. So we start by noticing that it's already got it 0 on one side, which is very nice. And I'm just going to go ahead and point out what we pointed out at the end here when we are finishing our problem. We want where it's positive, and we're going to use parentheses because there's no equal sign. So after we go through and do all our work, we'll look at where it's positive and use parentheses. So what we want to do is figure out the x-intercepts first. And that means set the numerator equal to 0. This one's actually a fraction, so saying that makes a little more sense. So we've got x squared plus 4x equals 0. Solve that. Well, we can factor the x out. So we got x times x plus 4 equals 0. And then set each factor to 0. We get x equals 0 and x plus 4 equals 0. And now go ahead, and this one's already solved for us. We got 0. The other one on the right, subtract 4, we get x equals -4. Now these two numbers are going to go on the number line, but because we have a fraction here, we cannot forget about doing the denominator as well. So we want to do points where it's not continuous. Because we're lifting up our pencil, it might switch there. So we have to set the denominator equal to 0 and solve that as well. We got x minus 5 equals 0. And that one's pretty straightforward to solve. We add 5 to each side and we get x equals 5. So we got 3 numbers here that we're going to put on the number line. We got 5, we got 0, and we got -4. Okay. Draw a number line over here. That's not very straight. That's good enough. We got, make sure you put them in order, -4, 0, and 5. And just like before, we want to pick numbers in each interval to plug in and do the sign thing. So I'm going to do -5, -3, 1, and 6. Just pick any number in the interval, but don't be ridiculous. I wouldn't plug in like -100. There's no reason to do that. So we're going to plug these numbers in. the original. And just record the sign like before. We got -5. It's -5 squared plus 4 times -5 over -5 minus 5. You only care whether it's positive or negative, so if you can see that, do it quicker like that. You can. If you want to do it in your calculator, that's fine too. We got -5 squared plus 4 times -5 divided by -5 minus 5. You get -1/2, -0.5. But the whole point is that it's negative. So we're going to put a minus sign above there. Next, I'm going to plug in -3. Once again, we're plugging into the original. And we got -3 squared plus 4 times -3 divided by -3 minus 5. And that we get 0.375, which is positive. Next number we're plugging in as 1. So we got 1 squared plus 4 times 1 over 1 minus 5. This is nice and small. I'll just do this one by hand. On the top we have 1 plus 4 is 5. And 1 minus 5 is -4. That's a negative number. We got a negative there. And then the last one we're going to plug in is 6. So we've got 6 squared plus 4 times 6 over 6 minus 5. And you might be able to tell this one's positive because we got 1 on the bottom, and on the top we got 36 plus 24 is 60. So we got positive at 6. All right, so once we've got our sign chart filled out like before, then we remember what we want. We want positive. We want the positive sections, and we want to use parentheses. So the positive one between -4 and 0. And then also from 5 all the way over, nothing stopping us from going over to infinity. All right, so our answer, we got -4 to 0. And 5 to infinity, all parentheses. But we are going to be solving inequalities in almost every problem in chapter 4, like I mentioned, and this is how we're going to be doing them. So make sure you practice them and don't try to do them just with your calculator now, because it's not going to be that useful going forward.